Hey, what's up, YouTube? We're back with another episode in this series, learning basic mathematics out of this book by Serge Lang, a really terrific book. It's kind of like high school math done right or done well. It's a proof-based treatment, like a real proof-based pure math treatment of all of high school math. So we are starting from the very beginnings. Last week we did videos on rules for addition, and now we're moving on to section 3 on rules for multiplication. Welcome if this is your first time. This beginning of the video, we're going to do a little small talk section and just do any kind of housekeeping that might be important. I think that the most important, this should be very fast, the most important question is, what about the cat? It seems like the vast majority of you all enjoy Luna being here, but not everybody. I will say that we do have a sizable number of comments. I've had a few, probably 5 or so comments of people who really don't like her, but then something like 50 people who really love her. So she can be distracting. I admit she will be distracting, and so will the other one sometimes. All right, so let me know in the comments if she is too distracting and too annoying, and I'll get rid of her. Secondly, probably not though. Honestly, she's not going anywhere. She's not going anywhere. Secondly, structure. This is the second. Well, this is the most common comment, besides just a lot of people saying that they love what I'm doing, and that's amazing. I can't believe how many people, we are introducing to mathematics here, or reintroducing. It's amazing. So thank you, everybody, for being here. But one of the top questions and comments is just structure. Like, some people are looking for more structure out of the show, and that's fair. I'm figuring this out as I go. I expected to film a bunch of lectures before anybody ever found them, and then by then I'd know what I'm doing. But right now I have to figure it out as I go. So the structure that I'm thinking is a section per week. So very predictably, work one section of the book at a time. It won't always be every single section in a row, but I will say what the next section will be next week. And we can predict that we'll be working one section of the book at a time per week. So this week, we're going to do 2 videos per week. One theory video, which is today, and then another video later on in the week with examples. And this is where I think I can provide some pretty interesting examples that are outside of this book. I do want to bring in a lot of my knowledge from other math courses, especially abstract algebra and number theory, places where we can get examples of some of these concepts and proof arguments in other mathematical contexts. And it's just a place where we can go deeper on examples, also work more exercises, and things like that. So today's a theory video, and in a few days later this week, we'll do an examples video as well. All right, then another thing, this is brand new. There's been such overwhelming demand and response and people asking to join the weekend study group, the weekend discussion group, that I've created a new secondary group. It's not as small and tight-knit, but it is here live streamed on this channel, and it's recorded, and you can watch those after the fact. It's a members only section that will be meeting on Saturdays. So if that's interesting to you, I hope you check it out. Okay, then finally, if you ever, this is right off screen. If you ever want to get to the playlist for this series, or if you want to share it with anybody, I have a new URL, mathasahobby.com. So that's it. All right. Thanks for that. Now, here's my motivation for today. The other day, I was practicing some mathematics, and I came across this problem. And I want to find ways to be able to calculate this without using the standard kind of multiplication table method. Is there a smarter, faster way in order to do these two multiplications and addition. So this is partly sort of the motivation. But really, the other day I was in the cafe, like a week or two ago, in the cafe working exercises and looking ahead into the book and looking at the exercises for this section. And there was a beautiful exercise that brought me back. It said like prove one of the theorems or something. And I saw this quote that just made me chuckle, silently, and I just enjoyed it so much when I read this. I was like, it's that guy again. Like Serge Lang is just such a romantic guy. He loves mathematics a lot, and he has a certain style to his writing. So the following three formulas are used constantly. They are so important that they should be thoroughly memorized by reading them out loud and reciting them, repeating them like a poem, to get an oral memory of them. This is going to be the final result of this section. If you're reading along in the book, you'll know the page that I'm talking about. But like, dude, have you seen any math teacher talking about math like this, like comparing a math formula to a poem? Yeah, it's so perfect. And I love it because I tell my students to repeat these things. I tell them to write them down again and again and again as muscle memory. So, have you ever thought of these equations as poetry? Dude, have you ever thought of this as poetry? I guess he didn't say it was poetry. He said that you should repeat it like poetry. But you should get an oral memory of these things. They are very important. A plus b quantity squared is a squared plus 2ab plus b squared. Same thing for the second and same thing for the third. Now, I feel like Serge Lang he's just missing an opportunity here, though. You can go a little further on this idea because it really is very valuable to try to get an oral memory of mathematics, of something like this. I think if you want to treat these like poems, one way to really go a step further on this is not the a plus b squared formula. This first one is the square of a sum. So if you take a sum and then square it, then this is the formula that gives you the square of a sum. And then the square of a difference is the second formula, right? That's a little more poetic. That's a little more conceptual. Like, we're not using A's and B's. Those are arbitrary. We could be using X's and Y's or emojis or something else anyways, right? And then the final one, the difference of squares formula. So these really are that important. And if we understand these and we can prove these, then that can help us solve this problem. Okay, so let's get started. Rules for multiplication. Intuitively, multiplication is as you remember, right? Like multiplication of integers is like repeated addition. 3 times 4 is 4 groups of 3. But that works for the positive numbers. But what would it mean to have negative times in like a sum? Like that definition that says that it's repeated addition requires that at least the second number or one of the two needs to be non-zero or non-negative. You can't have like a negative number of terms in a summation, right? So that requires b being greater than 0. So we need to get a little more formal and learn all of the rules and decide on exactly the rules that will work for multiplication, especially since we are inventing the negative numbers and we need to create a set of rules that still works, that still is compatible with the positive numbers. So more formally, multiplication is a function that takes 2 numbers and then returns another number. It takes a pair AB and then returns their product and their product needs to follow certain rules. So yeah, more formally, like we need to learn what those rules are. The first two rules are very similar to addition. We have commutativity. A times B is the same as B times A. And then secondly, we need to have associativity, just like in addition. A times B times C is the same as A times B, then multiplied by C. Okay, then for any integer, 1 times that number is itself. This is actually an assumption or not proved. I guess it, from the extension of multiplication being repeated addition, I guess this would be 1a in the summation, a without adding any other copies of a. So that makes sense intuitively. Like 1 times a is a, and then we have this other property, 0 times any number is 0. What's interesting is that we can prove this algebraically, that this fact that we're used to must be true. And so we will see that soon. I'll be working a bunch of proofs today, but first here's an example. Good old classic, this type of multiplication, 2a times 3b. So using associativity, we can regroup the parentheses. So I regroup the parentheses once, and then I regroup the parentheses again inside. So multiplying a times 3 and then b on the right-hand side, on the outside of that multiplication. Then we can use commutativity. A times 3 is the same as 3 times a. Then we can use associativity again. Associativity, again, if you don't know what that means, if you're not following my proof, be sure that you look at these rules that I call associativity. So this says that anytime that we have a product like 1 times 2 times 3 like this, we can regroup the parentheses. So that's an example of associativity. I regroup the parentheses to be around 2 times 3. And then finally, 2 times 3 we can multiply together to be a number times a times b. Lang then has some commentary about how this is very conventional and useful to rewrite products so that all the numbers are on the left and then the variables are following the concrete numbers. And that's a good idea. And it's usually a pretty good idea to also alphabetize the order of the variables as we go. Okay, let's keep going. We also have, I want you to pause and try to think about what these lines are going to be before I reveal them. What is another property about the numbers? This is not proved about multiplication, but we have distributivity. So we have this fact about multiplication. Multiplication connects with addition with this property, with this rule. The product of a sum is the sum of products. That's a way to say this one. The product of a sum is the sum of products. Like AB is a product of A and B. AC is a product of A and C. So this is a classic fact, and when we generalize the concepts of addition and multiplication to other mathematical number systems, this is one of these properties that we have to take as an axiom, as an assumption that you have two operations, addition and multiplication, and they connect together with this property. Something that's really cool, I think, is that if you assume distributivity, left distributivity, then we also immediately get right distributivity. So we don't have to assume both of them. If you just assume one, then you get the other automatically. So if you have a sum on the left and then you multiply it by a number, you can distribute on the right of a sum this way. So how do we prove that? In order to prove an identity like this, which Lang did not give this a name, but it is, I think that this is one that's worth referring to. In order to prove an identity like this, you typically want to start with usually the left-hand side and then keep rewriting it until it is rewritten to be the right-hand side. So, starting with the left-hand side, A plus B times C, using commutativity, I can swap this multiplication, right? Commutativity allows you to swap the order of a multiplication. So I can I can swap that order, and then I can now use left distributivity, which we assume works. And then now I can use commutativity again. C times A is the same as AC, and CB is the same as BC. And now we are done. We get to draw the cute little square. All right. Then we can also prove that 0 times anything is 0. I mentioned this earlier, and this one is interesting, I think. So 0 times the number A, well, in these algebraic proofs, a really powerful technique, like a really, really powerful strategy, is adding 0. Like usually like either adding and subtracting the same number, which is the same as adding 0, or multiplying something by 1. So I think that this one goes by adding 0 to it. I'm pretty sure it does, yeah. And now, so 0a is the same as 0a plus 0. Adding 0 to anything doesn't change it. That was a property from the previous section on addition. Furthermore, 1 times 0 is itself, right? 1 times 0 equals 0. Oh, okay, I did this one a little bit differently. Okay, well that other approach works too, but 0 you can write as A minus A, because whatever A minus A is also 0. This is, I said earlier, this is another one of those like overpowered strategies. You can add and subtract the same number. And now what I'm doing here is A is, I suppose I could have written in another line like 1A. I could have written 0A, 0A plus 1A minus A. And then I factored out on the right, so this is using right distributivity, that I can factor out the A, in other words, like reverse distribute is like what we mean by factoring A. So then 0 plus 1 times A minus A. Then 0 added to anything is itself, right? So 0 plus 1 is 1. We have 1 times A minus A. Next, we have 1 times anything is itself. That was assumed previously. And A minus A, again, that is the definition of minus A, or the definition of negative A. They add to 0. So, therefore, the left-hand side, rewrote until it equaled the right-hand side, and therefore 0 times anything equals 0. And it must equal 0, assuming mostly distributivity. Yeah. Okay. We can also prove that -1 times any number is the negative number. So notice that, yeah, this sentence is not, let's see, it's not as obvious as it seems or something. Like, we don't know a priori that the additive inverse of a number is -1 times that number. We don't know that must be the case. Yeah, we have to prove this. We have to prove this fact. And we do it here. So how do we prove that something is -a? What we want to show is that, let me go on a little detour here, because I think that this one is a little more subtle than the others. To show let's say, to show m is -n, if we want to show that some number is -n, oh, Luna, Luna, we must show that n plus m equals 0. For m to be the same as -n, it has to satisfy this property, that it is the additive inverse of the number m. So this is the strategy that we need to take in this proof. So I think I started writing that. To show that -a is -1 times a, we must show that a plus this thing, -1 times a, equals 0. So a plus this, -1 times a, is 0. So we have to, this is our game that we're trying to prove is true. So we start from the left-hand side of that equation and rewrite it until it equals 0. So let's take a look. A plus -1 times a, I think that I rewrite a as 1 times a by that previous property that 1x equals x, or 1n equals n for any number. Now I can distribute or factor a, and then 1 minus 1 is 0, and we previously showed that 0 times anything is 0. So we are done. Okay? Please pause and let me know. What do you all think? Any questions? Any questions? Pause, drop a comment in the comment section now. Let me know. I should have said this earlier in the small talk section. What do you all want to see out of this show, out of this channel? Like, I think that there's so many opportunities and so many decision points right now. I really want to get everybody involved. There's a lot of people interested in learning abstract mathematics, and that is my favorite thing. That would be so cool if I can get a lot of people interested in proofs. It's because it's just really, it's really fun. It's really pretty. Like, it's a game. Like, it feels so much like a board game to me, dude. Like, so please drop a comment in the comment section if there's anything you'd like to see more of or less of. More Luna, I hope. I hope that's the number one answer. All right, in particular, now this is cool. He doesn't call this a corollary, but I'll use the word corollary. I think he used the phrase in particular, but if you think about it, this fact must be true for any number a. In particular, it's true for a equal -1. So -1 times -1 equals negative of -1, right? So in particular, we can apply that previous general fact to show that -1 times -1 is negative of -1, which is +1. Proof. We apply N7 with A equal -1, as I just said. So we have -1 times -1 is negative of -1, which is +1 by N4. N4 previously said that a double negative is that the additive inverse of a number is the number itself. That's true for any number A, so it's true for the number 1 in particular. Cool. We also have this one. Negative of a product is negative A times B. We can prove that. We show that, again, we want to show that when we add this term to AB, that they add to 0. That shows, therefore, that negative A times B is negative AB. Like the number that is the negative version of A times B is negative A times B. That's kind of hard to say out loud, I feel. But I'm trying my best, dude. I'm trying my best. A, B plus negative A times B. So, yeah, we want to show that this sum equals 0. So that we can now factor out B on the right. We have that right distributivity property. And then by definition, yeah, A plus negative A is 0. A plus negative A is A minus A is 0. 0 times anything is 0. So now we are done. So therefore, we've shown this fact, which then, if we show this fact, which we just did, that says by definition, this term is negative of AB. Okay, similarly, there are two similar results in the book, and you can work these. For sake of time, I'm not going to work these because they're fairly similar, I think, to the other ones that we've done so far. And I really think it's worth, pausing and trying to work some of these on your own. And I can say, just pause the YouTube video and work it on your own, and don't resume it until you've finished. But I don't trust you to actually pause the video and work the exercises. So I'm gonna force it this time. If you want to see these proofs, try them, read them in the book, get the book. It's a great book. I do have an affiliate link now, so if you want to help me out, I gotta sell 3 of them in the next 6 months. Otherwise, they'll cancel my account. So I'm hoping that 3 people will get it from my link. All right, let's keep going. Next, we have powers that are defined. A to the n is defined as repeated multiplication, right? So the power, this is, we're defining exponentiation, an exponent. So with n terms in the product. So a to the n, 2 cubed is 2 times 2 times 2, right? Nothing surprising right now. But so then we say that a to the nth power is the nth power of a. yeah, this is the nth power of the number a. Then if m and n are positive integers, then we get this lovely formula that you may remember, and now we can prove it. So this is a counting argument. A raised to m plus n. Well, on this one, I thought it's cleaner actually to work from the right-hand side and then show that the right-hand side equals the left-hand side. You can go either direction in these proofs. On this one, I do think that's like a little easier to see. So a to the m is a multiplied by itself m times, and then a to the n, the nth power of a is a multiplied by itself n times, right? Now, if you regroup parentheses, if you drop the parentheses, how many terms are there? There were m on the left, n on the right, so then there's m plus n in total. There are, m plus n a's all in a row. And then, well, that is the definition of a to the m plus nth power. And then we're done. That's it. Okay, we have another rule for powers. We have this power rule. The power of a power is the product of powers. The power of a power is the product of powers. Something, is that quite right? Yeah. So a to the m raised to the nth term, this is going to be a to the m multiplied by itself n times. So we have n of these terms, a to the m, and there are n of them in a row. Well, each of those a to the m's are m a's, and there are n groups of m terms. So n groups of m is m times n. It might have been nice to write this as one extra line just to make sure that we totally see that. I think, okay, that's going to get kind of messy. So, yeah, if you just remove the double layers of, the counting labels, you would see that there are m plus n a's, because there's n groups of m terms, and n groups of m things is the product of m times n. Yeah. Okay. So now an example, we have this. This other fact is one that we get as an example or as a result. It's automatically true. This one is AB multiplied by itself n times. AB, n times. And then you can regroup by commutativity. There are n A's and n B's in this list. So remember we need to call out when we use commutativity. Fun fact is that in the future, we will work with number systems that are not commutative. So we need to know when we are using commutativity, and this is a place where we use commutativity to rearrange this multiplication. And yeah, the left one is a to the n, the right one is b to the n, and then therefore we're done. Hi, Luna. Sorry about my cat. Luna. All right, finally we get to our to our main conclusion here. Luna, hi. So, as I said before, we have these beautiful formulas. They're poetry. They're actually poetry. They really are, actually. And in particular, today, I just want to work the square of a difference. Well, here's the square of a sum. It's slightly simpler, I think, than the other one. The square of a sum, the sum raised to the second power is that sum multiplied by itself. Then you can use distributivity where you have x plus y times z, and z is all of a plus b. So I'm using distributivity xz plus yz. X is a, y is b, z is a plus b, and that gets us to your second line. A times a plus b times a plus b, and then you do distributivity again. A times a plus b plus b times a plus b times b. Again, here, note that we need commutativity. This doesn't work all the time in the future in some other weird, different math worlds, but here it does. So I used commutativity, and I just rewrote A using the definition of the second power. And then adding AB plus AB is 2AB. And then we're done. We've completed that formula. We can do the same thing for the square of a difference formula. So take A and B to be any integers. Then the difference squared is, by definition, the difference times itself. Now, what I did here is I rewrote negative b, or minus b, a minus b as addition of a negative. And that's because so far we've only proved distributivity laws for addition. We don't actually have distributivity rules that we can use with subtraction. And we should be careful because subtraction, some math facts break with subtraction, like subtraction is not commutative and things like that. So I want to make sure that we can use the tools that we've built so far, rewrite everything as additions as we go. So now the left hand side, or the first term, is now the sum of two things. Here I'm using x, y is negative b, and z is all of a minus b. Then x times z is here, a times a minus b. Y times z is all of this. Luna does not understand math. She doesn't understand math, but she's cute though. And then we do distributivity again. A times a minus a times b plus negative b times a plus negative b times negative b. A times a is a squared. Plus negative ba is the same as minus ba. Negative b times negative b is b squared from previous results that we have. Here I used commutativity. ba is the same as ab. And then finally, we're done. We're done. Yes, we're done. Hi. So, therefore, 1597 you can rewrite as 1600 minus 3. So I can square that difference, and it's easier to compute. 1600 squared minus 2 times a times b plus b squared. 16 times 16, you might know, is 256. they're powers of 2. So you could keep doubling until you get to 256. And if you multiply with 2 zeros, 2 zeros is multiplying by 100. 100 times 100 adds 4 zeros at the end of 256. The middle term, 2 times 3 is 6, times 1600, and then the last term is 9. Now I just doubled 1600 to 3200. 6 is 2 times 3. So I multiplied by 2 first. And then I see I can triple 32 in my head to be 96. And now 9600, I think of as subtracting 10,000 and then adding 400. So if you think of that as minus 10,000 plus 400, then this first number, notice that the 6 is in the 10,000th place. So you'd have whatever that is, 2,550,000 plus 9 plus 400, and that gets you this number. And we are done. That's it. Thank you, everybody. I've got cat hair absolutely all over me. Please do hit the like and subscribe if you haven't already. And yeah, really, let me know. Let me know what you'd like to see out of the series, and if you enjoyed this, if there's anything I could do to make it better for you all, because I think that this is an amazing thing that's happening. So thank you for being here, and take care. Bye. See you in a couple days with an examples video. See you soon. Bye.